Let's begin our discussion on work and energy. Let's assume that we have a particle moving along some path. And along that path, it's going to move over some distance. And we'll choose for now a very small distance, dr. Now that is a vector quantity. And in moving along dr, there could be a net force acting on the object. And since it's a net force, I'm actually going to draw this out in red to go along with my acceleration, only we'll multiply that by mass. So mass times acceleration is equal to net force, also a vector quantity. Then the amount of work in moving along that small distance dr in this pathway is an amount of work equal to du. And we define that work, so three equal signs because it's a definition, as F net dotted with dr. So this is a dot product. Very important, that dot product. We'll talk about that more in just a little bit. So as I travel along this entire path, let's say there's an origin here, and I'm going to go from position 1 to position 2. Then I'm going to have to integrate along this entire path. And so what happens is the net work in moving from position 1 to position 2 is equal to an integral of the net force dotted with the displacement dr. And our limits of integration are position 1 to position 2. So there's nothing that says the net force is going to be constant. In fact, as we look at that curve, it definitely is not going to be constant, because in order to make this turn here, I've got to have an acceleration in that direction. And in order to make this turn in this direction, I have to have some acceleration in that direction. It may be speeding up and slowing down, I don't know, but definitely not going to be a constant force. These integrals that we'll do will be easier in some cases than in others. All right, so again, the net work done is equal to the integral from R1 to R2 of the net force dotted with the displacement. Now let's talk about that dot product. Very important. Recall from vectors, if I have a vector A and another vector B, then the dot product of A and B is equal to the magnitude of A, which I'll write this way, times the magnitude of B, times the cosine of theta, where theta is the angle in between those two. But if you think about it, I can take B, here's A again, and there's a component of B in this direction. This is B cosine theta. And I like to write that oftentimes as the component of B parallel to A. And so A dot B is equal to A B cosine theta, which is A times the component of B parallel to A. We could do the same thing with a component of A. In this case, I have to extend B. There's a component of A here, A cosine theta. And that would be the component of A parallel to B. So this dot product then yields the component of A parallel to B times the magnitude of B, or the component of B parallel to A times the magnitude of A. So I can write it either way. Well, how does this come into play then? So let's take a look at an example of a child pulling with a 25 Newton force on their little red wagon. And we'll assume that this is at an angle of 53 degrees just to make life simple. The reason I use 53.1 degrees is that's a 3, 4, 5 triangle. And so my 25 Newton force breaks down into 20 newtons in the y direction and 15 newtons in the x direction. Now the luxury here is that there's then a component of the force, in this case 15 newtons, along the distance that I travel. Now we're going to assume delta r is equal to 10 meters. Why delta r? Remember that du is equal to F net dotted with dr. But if the net force is constant, and we'll assume the child's force of 25 newtons is the net force, if that's constant, then I can just write delta U, that's the work being done, is equal to the net force dotted with delta R. So the component of the force in the direction of the displacement is the 15 newtons. And so the work being done here, du, is equal to 15 newtons times 10 meters. Notice that work is a scalar quantity that's created by vector quantities. The dot product is oftentimes referred to as the scalar product. I could also write this as delta U equals 25 newtons, that's the net force, times 10 meters, that's the total displacement, times the cosine of 53.1 degrees. And that's going to be 250 newtons meters times the cosine of 53.1 degrees. But the cosine of 53.1 is 3/5. And so this would be 5 goes into 25 5 times, 50 times 3, which is 150 newton meters. Exactly the same thing I get when I multiply 15 newtons by 10 meters. So 150 newton meters. You can see the units here for work in the metric system are newton meters. In the English system, they'll be pound feet or foot pounds. I'll generally use pound feet just to be uniform. Newtons is force, pounds is force. Feet is distance, meters is distance. So I'll use pound feet. Alright, so if the force is constant, then the work moving from position 1 to position 2, pretty much what we just did. When I integrate the net force dotted with the displacement from R1 to R2, well, the net force is constant, so that comes outside of the integral. It's still a dot product. So R1 to R2 are my limits of integration, and this is dr. But that's just going to equal the net force dotted with delta R, or the net force dotted with R2 minus R1. So the constant force is pretty easy. The work going from 1 to 2 equals F net dotted with R2 minus R1. Well, let's pick another force, also a constant force. In this case, gravity near the surface of the Earth. Well, in this case, the force due to gravity is just minus mass times the acceleration due to gravity in the y direction, the j hat direction. And so irregardless of what my position is, when I take, that's a vector quantity, when I take fg dotted with delta r, this is going to be fg dotted with 2 minus x1 in the I direction, plus y2 minus y1 in the j hat direction, plus z2 minus z1 in the k hat direction. But fg is just minus mg in the j hat direction, and so by the rules of dot products, this would equal 0, because there is no x component of the force, times x2 minus x1, plus negative mg times y2 minus y1. Again, it's x component times x component, plus y component times y component, plus z component, which is 0 in the case of the force, times z component. And so in the end, this becomes minus mg times y2 minus y1, which is minus mg delta y. So the force due to gravity does work, and it's very simply equal to minus mg, the weight of the object, times the displacement strictly in the y direction. So it doesn't matter how much I go up or down or how I do it. I could have a spiral rising into some new position, and the only thing that really counts is this distance in here, and that's y2 minus y1. regardless of the path that I took to get there. Now, a force that is not constant is gravity far from the Earth. So we may remember from previous classes that the force due to gravity, which I'm going to subscript with a large G because it's gravity far from the Earth, is equal to G times mass 1 times mass 2 over r squared. That's the force due to gravity far from the surface of the Earth. But you have to keep in mind this is a vector quantity, but instead of using x and y coordinates, I'm going to use radial transverse system. All right, so imagine that I've got a mass 1 here, a mass 2 here, then there's a distance between them. That's r, and that's a vector quantity. And if I consider mass 1 to be my origin, then E sub r hat points out in that direction. And the force that mass 1 is exerting on mass 2 is pointing towards m1. That's the gravitational force. So it's inward. And since that force is inward, that means that there's got to be a minus sign out in front of that gravitational force, because E sub r points out and the force is pointing in. So it's in the minus E sub r direction. All right, so if I want to know the work done in moving from one position to another, then I'm going to integrate from r1 to r2 minus G mass 1 mass 2 over r squared E sub r dotted with dr, which is a vector quantity. Now let's say I'm moving from here, position 1, to there, position 2. So we'll label this R1, and we'll label this one R2. Then I can think of my transverse direction as this, kind of along a circle, and then my dr in the radial direction is that. So this would be dr transverse. This would be dr radial. So my integral becomes an integral from r1 to r2 minus g m1 m2 over r squared. I only really need, since it's a dot product, the radial component is the only thing I really need. So this becomes dr, and I can change my limits of integration to scalar r1 and scalar r2. In other words, all that really matters is how far did I move in. Again, the path that I take from 1 to 2 is irrelevant. We'll talk more about that later. So we can evaluate this integral as minus g m1 m2. And then the integral of 1 over r squared is minus 1 over r. And then evaluate that between r1 and r2. And so in the end, we get g m1 m2 1 over r2 minus 1 over r1.